Good morning, students. Myself, Vijay Shankar from ECE Department, Chevrolet Engineering College. Today, we are going to discuss about some more examples in the electrostatics in the unit 3. A parallel plate capacitor with a separation of 1 volts applied when air was used. When air was the dielectric used, assume that the dielectric strength of air as 30 kilovolts per centimeter. A thin piece of glass with epsilon r is equal to 6.5 with a dielectric strength of 290 kilovolts per centimeter with a thickness of 0.2 centimeters is inserted. Find whether the glass will break or air. See, this is a parallel plate capacitor. We can take the distance D1 is equal to 0.8 centimeters and D2 is a 0.2 centimeters. The applied voltage 20 kilovolts. We know the capacitance of the two parallel plate capacitor C is equal to epsilon A by the D. Epsilon A by the D is considered as epsilon naught 8.844 in 10 power of minus 12. A is the area of the plates and D is the distance between of the two plates, that is a D1. 0.8 centimeters is given, converted to the meters, that is a 10 power minus 2. Calculate this function, the C is equal to 1.1067 at 10 power of minus 6. A is there, it is not the ampere, my dear students, it's the area of the parallel plate. Farads. C in air, C in the air, let us treat the dielectric constant. Similarly, C in glass, C, the capacitance of glass is epsilon naught and epsilon r. Epsilon naught is the same. It is 8.854 in the power of minus 12. And D2, the distance here, the D2 distance in the glass is a 0.2 centimeters. So 0.2 into meters, you can convert 10 to the power of minus 2. And epsilon r is given, that is a 6.5. A thin piece of glass with epsilon r is a 6.5 with a dielectric strength of 290 kilowatts per centimeter with thickness of 0.2 centimeters is set. Now I find that is a C in the air with the distance of 0.8 centimeters and a C in the glass with the distance of 0.2 centimeters. We got the C glass is equal to 2.877 at 10 to the power of minus 8 A farads. A is the area of the plates. And C equivalent is the series, both are the series. C air and the C glass, they get C into C glass by the C plus 1. In the last class, I explained that is a 1 by C equivalent is equal to 1 by C1 into 1 by C2 is a parallel for the series in the capacitance. So C air we got and the C glass we got, you can substitute these values and you can find the C equivalent 1.0667 in 10 power of minus 9 A. A again, it don't think it is the ampere, that is a is an area and it is a C is in the farads. Let the area of cross section A is equal to 1 meter square. Let area of the 1 meter square, let us assume that is a is equal to 1 meter square. The C equivalent is given 1, can substitute here 1.607 in 10 power of minus 7 farads. The total charge Q is equal to C is equal to Q by V. You know the formula is there. The C is equal to Q by V. Q is equal to C into V. The C equivalent we got here. When I am assuming the area is 1 meter square, 1.0657 into 10 power of minus 19, 10 power of minus 19. And the voltage is 29 volts is applied in the 29K, the 29 in 10 power of 3. There is a charge is we got now this 3.0905 in 10 power of minus 5. Okay, my dear friends. The voltage V air is equal to Q by C air. You got the Q and the capacitance in air. We also got the ratio between of that. We'll get the V air is 27 kV. Glass. The total voltage V is equal to V glass plus V air, and the V glass is equal to V minus the air is 29 minus this one. We'll get the voltage for the glass 1.074 kilovolts. And we know the formula is that the electric field is equal to applied voltage and the distance between the distance of that one. So E air is equal to V air by the D1. The D1, the given is a 0.8 10 power of minus 2. We'll get the E air, and the E glass is a V glass by the D2. D2 is a 0.2 and 1.74. That is in terms of the kilovolt per centimeter, not the meters, my students. Is a centimeter, and here it is a meters. Why the 0.8 into 10 power of minus 2 there is a multiplied, and here it's directly substitute the 0.2. So it's a kV by the centimeters. Converting the air is also in the terms of the centimeters. 10 power minus multiplied here, it's a 10 power minus 2. Okay. So dielectric strength of air is 30 kilovolts per centimeters, and E air is more than that of, hence the air will be the breakdown. The dielectric strength of glass is 290 kilovolts per centimeters, and the E glass is less than that of the, hence the glass is will not the breakdown. If it is a more than, it will break down. If it is a less than, it is not the breakdown of the glass. Okay, my dear friends. Now the next example, the width of the region containing the epsilon R1, the figure here is 1.2 meters. Find the epsilon R1 if epsilon R2 is a 2.5. Find the epsilon R1 if epsilon R2 is a 2.5, and the total capacitance is given the 60 nanofarads. The width of the region containing the epsilon R1 in the figure here is a 1.2 meters. Epsilon R1 is given. Find the epsilon R1 if epsilon R2 is a 2.5. Okay. In this case, the dielectric interface of the is normal to the plates. Hence, the two capacitors form as a parallel. Given the diagram, there is a diameter is there. That is a 2 mm diameter of the plate. The D distance, two plates, not the diameter, sorry. The diameter distance of the two plates is a 2 mm. Same for the both the dielectrics. A1 is equal to 1.2 into 2, that is 2.5 meters square. And A2 is also the distance, it is a 0.8 into 2. Okay, 1.2. The totally the glass and the air here, without not showing any dots values here. There's a 1.2 into, that is a 2.4 into meters, and 0.8 into 2 is a 1.6 meters square. That is the area A1 and the A2. So the capacitance of the two parallel plates is C is equal to epsilon A by D. Now I am considering that is C1. C1 is equal to epsilon naught into epsilon R1. C1 is equal to epsilon into A by D actually. A1 into D1, that is epsilon, you can write it as epsilon naught into epsilon R1. A1 by the D1. We got A1 as a 2.4 meters. Epsilon naught is already know that is a standard value 8.85 for 10 power of minus 12. Epsilon R1. And simplify the function 1.062 10 to the power of minus 8 epsilon R1 is a farads. And C2, the C2 also, the C0 into epsilon R2 A2 by the D2. D2 is a 2. The D value, the total value you can take here, the 2 into 10 to the power of minus 3 is a milli. The distance then 1.7708 into the power of minus 8 farads of the C2. The C equivalent, you can add the two functions, C1 and C2, will get epsilon R1 C equivalent is equal to 60 nanofarads, given that 60 nanofarads, that's the total capacitance. At that case, find the epsilon R1, when we can use the epsilon R2 as 2.5, is a 2.5 here we are using 2.5 as epsilon R2, and we can find the epsilon R1 for the total capacitance given is a 60 nanofarads. 60 nanofarads is equal to 1.7708 in the power of minus 8 plus 1.062 in the power of minus 8 into epsilon. Simplify this expression, you get epsilon R1 is equal to 3.9823. Okay, my dear students. Coming to the next example. It is related to the energy stored function or energy density. Say a pair of 200 millimeter long concentric cylindrical conductors of radii 50 mm and 100 mm. Is outermost is a circle we have here, concentric cylinder with the radius here is A is given the 5 mm and the B is given 100 mm, is filled with the dielectric with epsilon is equal to 10 into epsilon naught, means epsilon R is equal to 10. A voltage is applied between the conductors which establish E bar is equal to 10 power 6 by R into AR bar. Calculate the capacitance, voltage applied and energy stored. So capacitance for the concentric cylindrical conductors, the capacitance formula is there, the 2 pi epsilon L by ln of B by A. The length of the capacitance is concentric circle is given 200 millimeters, and epsilon is also given the 10 into epsilon naught. That epsilon naught we already know, my dear students, 8.854 into the power of minus 12. You can substitute. B is a 10 mm, so not the 10, 100 mm. So 100 into 10 to the power of minus 3 is a milli, 50 into 10 to the power of minus 3. Calculate the C is equal. Okay, the capacitance is not a function of V and the R. It depends upon the dielectric and the physical dimensions for the coaxial cave conductors. L is given 200 millimeters, 200 10 to the power of minus 3. ln B 100 10 to the power of minus 3, 50 10 to the power of minus 3. Calculate the 160.518 is a picofarads. And E bar is equal to the relation between the V and D is a V is equal to the potential or the V is equal to minus E bar into DL bar minus the integral E bar is given the 10 power 6 by R into AR bar. Okay, now consider the DL also. DL bar is equal to, when is a cylindrical, means dr into AR bar plus d phi into A phi bar and the AZ. If it is a spherical coordinates, dr into AR bar and d theta into A theta bar plus d phi into A phi bar. Okay, these are the differential elements in the cylindrical and the spherical coordinate system. Here, the given the E bar is in the A bar direction only, so you can take the DL is dr into AR, dr into AR. That is equal to AR bar dot AR bar is equal to 1 minus the integral 10 power 6 dr by the R. So minus 10 power 6 is a constant, 1 by R dr is a 1 by R dr is a ln of R. The radius is upper limit is B and A. That is equal to minus 10 power 6 ln of B by E. or you can remove this minus here and substitute A by B ln of. Got it, my dear? Substitute the A value and the B value as 150. We'll get 693.147 kV. Got it, my dear? And also you can find that is energy stored W is equal to 1 by 2 CV square. We got the CV as 693.147 and C already we got 160.51 in 10 power of minus 12. WE is equal to energy stored, W is equal to CV square. In the magnetic field, it is a Li square. Okay, my dear students. So WE is equal to 38.5606 joules. Or otherwise, we don't know this formula, the 1 by CV square. We have the 1 by 2 the epsilon into E bar square. E bar is already given directly, and epsilon, substitute that epsilon is a 10 into epsilon naught. And dV is differential surface area normal to the R direction, because E bar is in the R direction, means R into dr d phi dz. Okay, dr d phi dz is a cylindrical coordinate system. Z is equal to 0 to L, and the phi is equal to 0 to pi, and R is A to B. R is a to B. Lower limit is A and upper limit is a B value. For that also, the energy stored will get the same 38.56. It is easy by using this formula. If we know the capacitance and the voltage, W is equal to 1 by 2 CV square. Got my difference. W is equal to 1 by 2 CV square. And with this, the conductors, dielectrics, and capacitors examples is completed. Then you go for the another example. These examples are related to the Laplace equation, Poisson's and the Laplace equation. We know the Laplace is del square V is equal to 0. Poisson's equation also. Determine whether or not the following potential fields satisfy the Laplace equation. V is given x square minus y square plus z square, and for the B is given, and the three terms is there. 3 voltages. Find the Laplace equation. It satisfies for the given potential or not. Del square V. Del square V. Del V we know that is a dou by dou x of V, dou by dou y of V plus dou by dou z of V. Del square means the second derivative. So dou square x square V, dou square y square V, dou square z square V. So first of all, we can take the first one. The potential V is equal to, the potential V is given x square minus y square plus z square. Okay. The first term, the del square V, the first derivative, x square derivative, the remaining is a constant part. X square, first derivative is a 2x, and second derivative is a 2. Okay. So dou square by dou x is a 2x here, the minus 2y and the 2z. In this function, x and z is a constant, is a zeros. In this function, y and z is a constant. In this function, x and y is a constants. So we'll get only the 2x, 2 minus 2y and plus 2z. Again, with respect to the x, we can apply dou by dou x is a 2. Dou square V is equal to, for the first term is a 2. Second term is a minus 2. And third term is a 2. So 2 to get cancelled, del square V is equal to 2. So it is not equal to the 0. Hence, V does not satisfy the Laplace equation. What is the Laplace equation? Means del square V is equal to 0, you have to prove. Laplace equation means del square V is equal to 0. If it is not equal to 0 means it is not satisfies the Laplace equation. And second one, V is given. V is equal to R cos phi plus Z. R cos phi plus Z. So del square V is equal to, because it is a cos phi and the Z means take it as a cylindrical coordinate system. That cylindrical coordinate system is 1 by R dou by dou R of R into again the dou V by dou R plus 1 by R square into dou square V by dou phi square plus dou square V by dou Z square. Okay, my dear students. So actually it is a 1 by dou R dou V by dou R plus 1 by R into dou V by dou phi and dou V by dou Z only. Because it is a del square 1 by R into dou by dou R of R into dou V by dou R. What is a dou V by dou R here? Cos phi, the Z is a constant. So first term we can take it as a 1 by R into dou by dou R of again R into dou V by dou R. Cos phi will get here when I am applying the dou V by dou R as the first derivative. And again we can apply here the dou by dou R with this derivative of R, the cos phi only. So 1 by R cos phi for the first one. 1 by R cos phi. Got it, my dear students? You see here. So dou V by dou R is equal to dou V by dou R is equal to. So R into dou V by dou R is equal to. That is R into R cos phi plus Z. Dou V by dou R only. If I am taking the dou V by dou R, R cos phi plus Z cos phi. Okay. And dou V by dou phi. And directly I am substituting the 1 by R into cos phi here. This is the first term, total first term. And here they are showing only the dou V by dou R, dou V by dou phi, and dou V by dou Z. Dou V by dou phi is R cos phi plus Z is equal to, Z is a constant, is a 0, and R is also constant when you are applying with respect to the phi. Cos phi is a minus sin theta, or the sin theta, cos sin phi, minus or sin phi, and 1. And these functions, cos phi, r, minus or sin phi, and 1, you can substitute to get in this function. The first term, see here, the 1 by R dou by dou R, R into dou V by dou R is equal to 1 by R cos phi. 1 by R cos phi. And second term, the second term, what is the dou V by dou phi? We got a minus or sin phi. The second term we can take 1 by R square into, first of all, if I am apply for R cos theta plus Z, first derivative dou by dou phi of what will get R into cos phi, the derivative is a minus sin phi, minus sin phi. Okay. Plus for this function totally R, again you can apply the derivative the cos phi. Cos phi, R get cancelled, 1 by R into minus cos phi. Okay, plus dou square V by dou Z square. So dou by dou Z is a 1, and again it is a 0. So 1 by R cos phi minus 1 by R cos phi get cancelled. So del square V is equal to 0. It satisfies the Laplace equation for V is equal to R cos phi plus Z. R cos phi plus Z. Okay, my dear students. So this field satisfies the Laplace equation. And the last one, consider the V is equal to R cos theta plus phi. Means it is a spherical coordinate system. In the spherical coordinate system, del square V is equal to, this is a formula that del square V is equal to. So 1 by R square dou by dou R of R square dou V by dou R. Previously it is a 1 by R only. And here also 1 by R square but it is r square sine theta is multiplied because in the differential element r sine theta d phi. Okay, so 1 by r sine theta, dou by dou theta of sine theta into dou v by dou theta, 1 by r square sine square theta, dou square v by dou phi square. So use this formula to find a Laplace equation by substituting the value of voltage V is equal to r cos theta plus phi. First of all, dou V by dou R. Dou V by dou R means cos theta. You'll get the cos theta here. R square cos theta. Okay. Dou V by dou R means R is a 1 cos theta. R square cos theta. Dou V by dou R again you can apply here. Cos theta is a constant with respect to the R, 2R. So 1 by R square 2R cos theta is the first term. So R and R get cancelled. 2 cos theta by R. 2 cos theta by R is a first function. Okay. This is here. 2 cos theta by R. Del square V. R square and 2R cos theta and R square get cancelled. R get cancelled. 2R cos theta by R. This is the first term. For this first term, the answer is a 2 cos theta by R. For the second term you can see dou V by dou theta means cos theta is a minus sine theta. Minus sine theta and R is a multiplication factor. And again, this sine theta is multiplied with this another sine theta, sine squared theta. Minus R into sine squared theta. Again, you can apply the dou by dou theta. Minus R is a constant, sine squared theta, 2 sine theta, minus cos theta. Okay. 2 sine theta, and so minus not sine theta is a cos theta only. Cos theta. So minus R cos theta. Again, it is multiplied with 1 by R square sine theta. R and R it is get cancelled here. Sine theta and sine theta is also get cancelled. Now it is a minus 2 cos theta by R. That is the second term after simplifying this total function. It's a minus 2 cos theta by R. Once again, I will explain. Dou V by dou theta means dou V by dou theta. It is a R is a constant and cos theta is a minus sine theta. Minus sine theta is multiplied with this sine theta. I will have minus sine square theta into R. Again, you can multiply, apply the derivative with respect to the theta. R is a constant and minus, you can write a minus R. Sine square theta is a 2 sine theta cos theta. And it is multiplied with 1 by R square sine theta means minus 2 cos theta by R. That is the second term. Coming to the last term, dou square V by dou phi square. Okay, first of all, you can apply the dou by dou theta, not the theta phi, and dou by dou phi of V. What is the V? R cos theta plus phi. So first derivative of phi is a 1. So dou by dou phi of 1 and dou by dou phi of 1 is a 0. The 0 into 1 by R square sine square theta is also the 0. Totally the last term is a 0. So 0, 2 cos theta by R and 2 cos theta by R plus and minus is both are the zeros. Then finally the del square V is equal to 0 for this function V is equal to R cos theta plus phi. And it is also satisfied. The third one is also satisfied. The del square V is equal to 0. So this field satisfies the Laplace equation. Got it, my dear students? Given the three potential V is equal to, the first one is not satisfies the Laplace equation, and second and third one is satisfies the Laplace equation, that is the del square V is equal to 0. And next example, verify that the potential field given the below satisfies the Laplace equation or not. Given the potential is here, the Cartesian coordinate system. So del square V is equal to dou square V x square, dou square V by dou y square, dou square V by dou z square. And here also, whether it satisfies the Laplace means del square V is equal to 0. Got it, my students? So first term, if I am taking dou square V by dou x square, in this the first term, the first derivative of 2x square is 2 into 2x. Okay. And again, the second derivative, the value becomes a 4. For the first one, the value is a 4. For the second term, first derivative is minus 3 into 2y. First derivative. And minus 3 into 2 is the second derivative. It becomes of minus 6. So for this, the second derivative is a minus 6. And the third function, first derivative is a 2z. Second derivative is a 2. So for this, we'll get the 2. So adding of all the terms, so 4 minus 6 plus 2, it becomes a 0. 4 plus 2 is a 6. 6 plus minus 6 is a 0. So del square V is equal to 0. It satisfies the Laplace equation for the given V is equal to 2x square minus 3y square plus z square. Okay, my dear friends. Coming to the next example. The region between the two concentric right circular cylinders contain a uniform charge density rho. Solve the Poisson's equation for the potential in the region. Okay. We already derived this expression, the potential Poisson's equation for the two concentric right circular cylinders. Again, once again, you can see, select the cylindrical coordinate system in a coaxial cable like structure. The electric field intensity E bar in radial direction for the inner to the outer. So inner radius is there and outer it is another radius. Here E bar and the V both are the functions for only R and not for the phi and the Z. So dou V by dou R is existing, while dou V by dou phi and dou V by dou Z is not existing. Those are zeros. According to the Poisson's equation, del square V is equal to minus rho by epsilon. Okay, my dear friends. So del square V, it is a phi and the Z means concentric, that is a cylindrical coordinate system. 1 by R dou by dou R into dou V by dou R is equal to minus rho by epsilon, because there is no any phi and the Z. Only I am taking the first term. 1 by R dou by dou R of R into dou V by dou R only. Okay, my dear students. And let's multiply this R here. Dou by dou R of R into dou V by dou R is a minus rho R in by the epsilon. Integrating on both sides. Or apply the integral on both sides. We'll get R into dou V by dou R means here you can apply the integral and here is apply the integral of derivative or integral of partial derivatives are getting of constant. That constant is R into dou V by dou R. Integral is minus rho R by epsilon into dr, because it is taking that is a dr or dou R. Okay. Again, you can take this R here. Okay. C1 is a constant. Dou V by dou R is equal to minus rho by epsilon R by the 2. R by the 2 function. See, that will get as of is here this is an integral term, and there is another value is R into dou V by dou R, and as a C1 is a constant of the integral, we can take dou V by dou R is equal to, dou V by dou R is equal to, is a constant you can take, is a constant, apply the integral of R, that is R square by 2. Integral of R is R square by 2 minus students. Becomes of R dou V by dou R is equal to minus sigma by rho by the epsilon naught integral R into dr. Is a function actually. That is equal to minus rho by the epsilon naught. R integral is R square by 2. And cross multiply this R here. Dou V by dou R is equal to minus sigma rho by the epsilon naught R square by the 2R. R and R get cancelled. Minus rho R by the epsilon. And you can add that is a C1 as a constant of integration, dou V by dou R. Okay, my dear students. This is a value you'll get to minus rho by the epsilon into R by 2 also there. 2. Now the integrate on both sides, because it's the left hand side, there is a derivative is there. V is equal to integral minus rho by the epsilon naught by the 2. Got it, my dear students? V is equal to, that is a V is equal to, again is a C2 is a constant, minus rho by the epsilon. Here another integral is there. Integral, apply the integral. V is equal to minus rho by the epsilon 2. Integral dr, R with dr is a R square by 2. That is equal to minus rho by 4 epsilon into R square. See the voltage V is equal to minus rho R square by 4 epsilon. Knowing that boundary conditions C1 and C2 are the prime. Okay, so no need of this one. So directly we know the V is equal to minus rho R square by the 4 epsilon. Got it, my dear?